Hello and welcome. You ever stop and wonder why some things are super shiny and others are just not, like perfectly matte? Well, the answer is all about how light behaves, and it's all explained by this really cool principle known as Lambert's law.
I mean, it's something you see every single day, right? You can see a reflection perfectly in a mirror, no problem. But a painted wall with that same color? Nothing. No reflection at all. Now, both surfaces are bouncing light back at you, so what's the deal? That's the exact mystery we're going to unravel today.
So, to really get to the bottom of this, we first have to talk about the two main ways a surface can play with light. This is pretty much where the whole story of shiny versus matte kicks off.
And here it is, broken down perfectly. On one side, you've got specular reflection. The best way to think about this is like a pool ball hitting the side of the table. It bounces off at a perfect, predictable angle. One angle in, one angle out. That's your mirror. But on the other side, we've got diffuse reflection. This is more like throwing a handful of glitter at a wall. It just goes everywhere. And that scattering, that's the secret sauce for matte surfaces.
Okay, so if all that scattering is the key to a matte surface, let's zoom in a bit. Let's really figure out what's going on under the hood. We're moving from what it is to how it works. So here's the official definition for you. When a ray of light hits a diffusely reflective surface, it doesn't just bounce off cleanly. No, that surface is actually microscopically rough, so it takes that light and just throws it in a million different directions. And that is what stops a sharp, mirror-like image from ever forming.
And that scattering leads us to this really fascinating property called Lambertian reflectance. Now, this is basically the ideal, perfect version of a matte surface. Imagine a sphere that's perfectly matte. Because it scatters light so evenly, it doesn't matter where you're standing, it looks like it has the exact same brightness all over. There's no glare, no hot spot. That consistent look is the main idea here.
So, how do we actually describe this perfect scattering with, science and math? Well, that brings us to the star of our show today, Lambert's cosine law. Okay, I know, that sounds a little dense. Radiant intensity, cosine of the angle. What does that even mean? Don't worry, we are not going to leave you with a dry textbook definition. Let's break this down.
See? Much better. Think about it like this. You're shining a flashlight on a wall. When that beam hits the wall straight on at a 90-degree angle, you get the brightest, tightest spot of light, right? But as you start to tilt the flashlight, that spot gets dimmer and more spread out. Well, that's it. That's Lambert's law in action. The brightness you see totally depends on the angle of the light source.
And just so you have the whole picture, you might hear this law called a couple of other things, like Lambert's emission law or the cosine emission law. They all describe the exact same principle, just using slightly different words.
All right, that's enough of the theory. Let's talk about where this stuff actually shows up in the real world. I mean, where can you see this happening every single day? Well, the most obvious one is matte paint. It's literally designed to create that soft, even look by maximizing diffuse reflection and killing that shiny glare. Frosted glass on a light bulb does the same thing. It scatters the light to give you a soft glow instead of a harsh, blinding point. And get this, even our own eyes use diffuse reflection to help process the light that comes in. How cool is that?
Let's just hang on that frosted glass example for a second. Because as you might have guessed, that soft glow is pretty much a perfect, real-world demo of diffuse reflection. Yep, 100% true. The surface of that glass is made rough on purpose, on a microscopic level. So when the light from the filament inside hits that surface, it scatters like crazy in all directions before it even leaves the bulb. And that's what gives us that nice, pleasant light that doesn't hurt to look at.
Okay, so we've looked at the what and the how. Now it's time to tie it all together and ask the big question. Why does any of this matter? What's the main takeaway from all this science?
So let's really nail this down. If you're going to remember one thing about a perfect matte surface, what should it be? It all comes down to one simple, elegant property.
That's it, right there. It's all about uniform brightness. A perfect matte object looks just as bright no matter which way you look at it. And this is exactly why artists, photographers, and interior designers love matte finishes. They give you consistency, softness, and you never have to worry about a distracting glare.
And this isn't just some artsy visual idea. It's something scientists can actually measure. The term for it is luminous flux. You can think of it as a way to measure not just the raw energy of light, but how bright our eyes think it is. It's the perfect bridge between the hard physics and our own human experience.
And here's the thing. This principle is so fundamental that it's actually built into our digital world. Physicists and computer graphics artists use super complex calculations, all based on Lambert's law, to simulate how light works. So every single time you see a realistic-looking matte surface in a video game or an animated movie, it's this very science working behind the scenes to make it look real.
And that's where we'll end it. You now know the science behind why things look matte, why a piece of paper, a painted wall, or even a clay pot looks the way it does. So the next time you're just looking around a room, check out the different surfaces. Now that you've got Lambert's law in your back pocket, how's that going to change the way you see the world? Thanks for joining.